grade 10 Mindsetters, welcome to today's Physical Sciences show. Today we have a special revision lesson on atoms, elements and compounds. We have selected highlights of lessons shown early in the term to help you revise Term 1's work. Please post all your questions and comments on our Facebook page on facebook.com/LearnExtra or on Twitter @LearnExtra so we can help you with your revision. Don't forget to download today's show notes on learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with our lesson.
We're now going to take some time to answer some questions. So, have a look at this one. Consider the following atom and answer the questions that follow. Now, they're giving this to us in standard notation. We have X, some unknown element, 24 and 12. Firstly, how many protons does this atom have? Now, protons, we're thinking, definitely we must come across and say, okay, the protons must be this number at the bottom. So it will be 12 protons. How many neutrons does this atom have? Well, in this case, it was 24 minus 12. Why? Well, because I had to take the number at the top, the atomic mass, minus the atomic number. And it doesn't always have to be the same number. In this case, it is. Because it's equal to 12. In this case, it happens to be 12 and 24 minus 12 is 12. But remember, this is the number of nucleons. That's inside the nucleus minus the number of protons, and that's going to give me only the neutrons. Write the chemical, let me write out neutrons. Write the chemical name for this element. Okay, so now we've got to go across to our periodic table. And how are we going to find it? Well, we've been given quite a lot of information. Can I come across here and say, let me go find 24 on the periodic table? Not necessarily, because that is not a definitive for any specific element. Rather, it could be an isotope, and it might not be directly on the periodic table. So, instead, where do we go? We go to this number, the atomic number. And that atomic number is going to be helpful in that it's the number of protons. That atomic number is listed on the periodic table, so let's go and find it. Sorry, let's just close that one down. We've got to go and find it and see if we can find it. We've got number 12. So notice I'm now looking at the top number, which is the atomic number. 1, 2, 3, 4, all the way to number 12. There it is. And this symbol is magnesium. So I go back to my table here, my questions, and I answer. The chemical name for the symbol for this element is magnesium. Okay, if they asked you for the symbol, it would be Mg. But they specifically asked us for the name, so it's the whole word. Now they asked me to draw an Aufbau diagram. You may see this in a textbook as rather saying not an Aufbau diagram, but an energy level diagram. In olden days, it was specifically called Aufbau diagrams. Aufbau means building up, and it can be quite a useful term. But rather, we're going to speak about how these electrons are arranged in their energy levels. So with the orbitals within these certain energy levels. That can be very, very useful to do. So they're asking us to draw that. I'm going to need a bit more space. So I'm going to come across to the bottom here and give myself a little bit more space to do this. So let's go down there And I'm going to start by doing a blank energy level diagram, and then we'll come along and fill in the electrons. So I start at the bottom with 1s and give myself a block. Then 2s, also a little block. Next comes 2p, and we've got 3 orbitals, 3p orbitals, so there's the blocks. Then I go to 3s, and these are representing, and 3p, okay? These are representing orbitals. Now the s orbitals stand for spherical orbitals, spheres, like a whole ball shape, right? In comparison, the p orbitals are dumbbell shaped, like almost like a figure of 8. And there are 3 of them because there's one going vertically, one going horizontally, and one going in and out the page. Remember, this is atom is a 3-dimensional structure. All right, and those are the regions of space where an electron could be found. So, firstly, I want you to notice that we've got 3 energy bands. Notice, and I'm drawing little dotted lines across here because I want you to pick up that this is going to be the first energy level, the second energy level, and then the third energy level. And it will continue, 4, 5, etc. Within those, notice we've also got orbitals, which are regions of space where those electrons could be found. This is a more detailed focused look, as opposed to those concentric circle ball models that I did earlier, where we just had 2 in the first, 8 in the second, 8 in the third. Okay? Still follows the same kind of pattern, or gives us a similar pattern, but it's more detailed. So notice we were doing magnesium, and we were asking for an atom of magnesium. I'm highlighting that for you because an atom is neutral. So down at the bottom here, I'm writing Mg, and it was 1224. That means it must have, because it's an atom, it is neutral, which means it's got 12 protons, therefore it must have 12 electrons for this thing to be balanced out electrically with no overall charge. So 1s can take a maximum of 2. 1 arrow up, 1 arrow down. That's because they have opposite spin. That energy band, that energy level is now full. So we've got to go to the next energy level. 2s, 2. Then we fill these up individually. And that is because electrons, they repel each other, and so if they can take their own orbitals. That would be great. They will. But we've got to fill a total of 12. So 1, 2, 3, 4, 5, 6, 7. Instead of going to the next energy level up, it will fill up with a neighboring partner. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we've got to go to the next energy level. 11, 12. So that has indicated to me the energy level diagram. But I can also write that more simply, and I don't know if the question asked me, showing the electron arrangement. We just had to do Aufbau diagrams. 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 3s2. And in a sense, I actually don't need to have that final top one here because it's not filled. So we don't even need to show that. Okay, or it hasn't got any electrons in it. So that was question D. Would this atom form a positive ion or a negative ion when this atom bonds? Provide a reason for your answer. So that's going to come back to looking at this structure. And remember, when atoms bond, they always want to have a filled outer energy level. So option here is to go and fill up, and I took it away, but I shouldn't have. I could have filled up with another 6 more electrons that would fill the next energy band, the energy level, the 3p, and the third energy level would be filled. But how many would it need? It would need 1, 2, 3, 4, 5, 6. A whole 6 more electrons, far too much effort. Not quite. But it could be done, but highly, highly unlikely, because energy, it's all about energy at the end of the day. Instead, those valence electrons, these ones here, are the valence electrons because they are in the outer energy level. There are only 2, so therefore it could lose 2 electrons and form a positive ion. And that's what it would do when it bonds. So it would lose 2 valence electrons, therefore would form a positive ion. Because instead of filling up another 6, it could get just to lose those 2 valence electrons. So it would form a positive ion. And that's the last of that question. Can we move on to question 2? Give the electron configurations and Aufbau diagrams. Again, we said these are energy level diagrams for the following elements. Once again, we've got it as an element, aluminium there. Let's go and fill in, and I'm going to start at the bottom, 1s, 2s, 2p, 3s, 3p. I'm not going to have enough space. Let me start this again quickly. I'm going to start a little low, 1s, 2s, 2p, 3s, 3p. Draw in my little boxes. 1, 2, the second energy level has got there, 3s, 3p. Okay, so for aluminium, I need to go find it on the periodic table. So, if we go to the periodic table, let's find aluminium. I know it is over there, and it's got 1327. The 13 is the number of protons, so I'm going to write it now in standard notation. Watch out. We're going to write aluminium, 13 number of protons, 27 number of electrons, 27 mass number, which is therefore telling me 13 protons, 13 electrons. Why? Because this is an atom and it's neutral. 13 protons must be balanced out by 13 electrons. In this case, it's going to be, well, how many neutrons? And I'm just doing this to show you and guide you through it. It would be 27 minus 13 gives us 14 neutrons. So coming back here, I could put in 14 neutrons. What I'm focused on, though, is I'm wanting to fill in the electron configuration. So 1s is going to have 1, 2, 2s, 1, 2, 2p, 1, 2, 3, 4, 5, 6. That's now 2, 4, 6, 8, 10. But I'm still trying to get to 13. So we have 1, 2, 3. That's my total of 13. Now, once again, aluminium would be easier for aluminium to lose all 3 of those valence electrons as opposed to gaining an extra 1, 2, 3, 4, 5, gaining an extra 5 to get its filled out energy level. Next one. Oh, I don't think we've finished. We haven't done electron configurations. Now, that's a slightly shortened way of writing because to draw these things out can take a bit of time, if you'll agree with me. So, instead we can write them in shorthand, and in doing that we can say, well, it's got 1s. How many of them? 2. It's not a power, but it's a superscript, so above the line and much smaller. 2s, 2, 2p. It's going to have a total of 6. 1, 2, 3, 4, 5, 6. 3s, 2, and 3p. See, not plus, but 3p1. That should take us through to our total, our electron configuration. Okay, and sometimes it's very useful to write it in shorthand. So you might see that in textbooks, because we can write it in one line rather than drawing a nice big massive diagram. Let's try the next one. So we asked to do an oxygen ion, and that word that I'm emphasizing is crucial, because an oxygen ion is not just an oxygen atom. It's now a charged particle. So how would it be charged? Well, let's go across to our periodic table and identify where oxygen is. There it is. It's got 16 and 8. So I'm coming across here and I'm going to write 16 oxygen. Oh, sorry, wrong way around. 8 at the bottom, oxygen, 16. What does that tell me? Well, I'm just going to then say, hold on, if this is an oxygen ion, it's not got the same number of protons as the same number of electrons. Instead, it's going to have more electrons. Why would it have more electrons? Well, what are we trying to get to? A filled outer energy level. So what we're trying to get to is the state of these noble gases, because that's when a substance would be most stable, if it's got a filled outer energy level, which means that it's going to take up an extra 2 electrons. So 1, 2, that would get that to the same as the state of the noble gases. So coming across here, again, we said, all right, well, it will have 8 protons. And do you agree with me that it would have 8 neutrons as well? I'm not going to write the neutrons in. But what I am going to do is identify that overall, it must have an extra 2 electrons, which means its charge is 2 minus. And I would go across to this standard notation, and at the top right-hand side, write in there 2 minus. That is now a charged particle. That is no longer just an atom, but rather it is an ion, because it's going to now have a charge. So when we draw in up this energy level diagram, we've got to take into account that this is going to have an extra 2 electrons. So I'm going to start 1s, 2s, 2p, 3s, 3p. I could continue, but I think it's going to be enough. We draw in our little boxes. Let's just draw them slightly smaller. 2s, 2p. Okay, I think that should be enough. Let's start filling them in. Well, we've got 1, 2, 3, 4, 5, 6, 7, 8. Now, I'm not stopping there, but what I am doing is just identifying that, and I'm drawing them in one color, and I want us to then say, those are the electrons that the oxygen originally had. Now, you don't have to change color, absolutely, you would just do this as you continue drawing, but I'm wanting to highlight it to you, because originally the oxygen atom had 8 protons and therefore 8 electrons. But now that it's charged, it's an ion, it's gained an extra 2 electrons. Those electrons, where would they fit in? 1 there and 1 there. And now it's got a final, more stable, filled outer energy level, because it has gained 2 electrons. And so it's now an ion. And I've highlighted them to you in a different color just to show you that that's where it would fit in. It's now filled outer energy level. That second energy level is completely full. So I hope that's really helped. we're going to come back and carry on with some more questions.
Alright, Mindsetters, I hope you guys are enjoying this revision session. Remember, if you are struggling and need help, please post your question on our Facebook page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, so don't go anywhere, we'll be right back. Welcome back, guys. I'm sure you've seen and heard about the Mindset Rack nomination and hope you'll get involved. If you make a video, post it on YouTube with the title #LearnExtraRack followed by your name or the name of your group. If you don't have a video, post a photo on our Facebook page and tell us what you've done. Let's use this short holiday to make a big difference in other people's lives. Now, let's get back to revision.
Let's go across to improving your skills, because these are the kind of questions that maybe you could come across and see. So, consider the following electron configurations and answer the questions that follow, using the letters A to E where appropriate. So we've got a list. And this list is giving us a whole bunch of electron configurations for different atoms. And that's, I think, what the question originally said. It would specifically have to be for atoms. And I think I need to add that in here. Because if it wasn't an atom, then if it was an ion, a charged particle, then it could have a different number of electrons. And so we wouldn't necessarily be able to answer the questions. But if these are all atoms, they're all neutral particles, they all have the same number of protons as electrons, that would definitely be something we could do. So here's our list. And when we answer the questions, I'm going to answer A, B, C, D, etc. Okay? So, and I've thrown this in here because I know students don't often like these electron configurations. They can be tricky. But hopefully, if you've thought through what we just spoke about in terms of the periodic table and the way it's arranged, we should be able to answer quite a few of these. So, the first question says, identify a halogen. Now, what is a halogen? Halogen is something that is in group 17 or group 7, depending on which way you're considering it. It would have, therefore, 7 valence electrons. Which means what? Because 17, remember we said 17 minus the 10, the transition elements. So group 7 or group 17 will have 7 valence electrons. Now I need to go across and do my counting. So I'm going to come along here and pick how many valence electrons in the third orbital there. It's going to have 6 valence electrons. How many there? Well, this one will only have 1 valence electron. What about here? This is going to have 3s2, 3p5. So the 2 plus the 5 will be 7 valence electrons. And I found my answer. It's going to be option C. Identify a halogen, option C. Have a look at the rest of them. Only 2, 6, 1. So no, none of the others fit. But I want you to pick up here that we were counting the whole of the last energy level, which means everything in the third energy level for the first one. It's not just 4, but rather 4 plus the 2, which is giving us the total of 6 in that valence outermost energy level. So watch out for those. Great, the first one done. I'm just going to clear these away so that we can make sure we've got space to answer these. Which element is found in the second period and the third group? Okay, so second period is going to mean, how do the periods link up with these electron configurations? Second period, or the second row, is going to mean that it's in the second energy level. So I need to write that down. That's going to mean second energy level. because the period links to the filled outermost energy level, which is, or the outermost energy level, which is the same as the period. And then they tell us the third group. Okay? Or maybe the question should have been rephrased, the 13th group. Well, have a look at it. We've got to come across. We said second energy level. So A is out, because it's in 3. B is out, it's in 3. C is out, it's in 3. Do you follow how we're doing this? We're looking for where does it end in the second energy level. D is an option. E is an option. F is an option. But we've only just done the first part, the second period. What about the third group? Well, the third group means that it's going to have 3 valence electrons, because it would be 1, 2, transition elements, 3. Okay? So, or we could have, and I'm going to write in here, or group 13, depending on how the question was phrased. Now I need to come across. Where would D fit in? D would fit in 1s2, 2s2, which means, and I'm going to jump across here, it would be it would fit in 1s, 1s2, 2s1, etc. Let's keep going. It would be the third group. It would have to be fitting in with 3 valence electrons. So notice here, that's going to have 3 valence electrons. This one is going to have 8 valence electrons. This one only has 2 valence electrons. So my option must be F, because it fits both criteria. It's in the second period, which means the second energy level, and it's in the third group because it's got those 3 valence electrons. So my option there is F. Identify an alkali earth metal. Now, alkali earth metals, you need to know the names of a few of these groups. So group 1 is the alkali metals. Group 2 are the alkali earth metals. So here we have, this must be in group 2, which means, therefore, that it must have 2 valence electrons, or outermost electrons. We don't know the period that it's in, but we do know that it can only have 2 valence electrons. And I worked some of these ones out earlier, so I can just take those away and head back here. This was 6 valence electrons, that was 1 valence electron, 7 valence electrons. The only one that fits, there it is, it's got 2 valence electrons. I'm going to just circle that slightly more better. There you are, 2 valence electrons. So my next option must be D. Do you recognize that although my final answer is actually only 1 letter, I still need to do a bit of thinking. And that thinking, don't just throw letters around. It really is about thinking and reasoning it through. So make sure that you do that. Which will form positive ions when they bond? Now, in order for something to form a positive ion, what's it going to have to do? It will have to give away its valence or outermost electrons. Okay? Which ones will do that? Well, they're going to form positive ions. Which ones will form positive ions? When they only have 1 or 2 to give away. So, options here are things with only a few valence electrons. We said, and I'm going to write these in here again, this was 6 valence electrons. 2 plus 4 is the 6. This one only had 1 valence electron. Now, going back to these, it's helpful to recognize when things bond, that they're going to want to have a filled outer energy level. So which is the shortest route to get a filled outer energy level? When those that only have one valence electron or two valence electrons, they're going to have to gain, for one, an extra 7 valence electrons to get a filled outer energy level, or for two, an extra 6 valence electrons to get to that filled outer energy level of 8. Instead, if they give away, then they can go revert down to the lower energy level, and then that is filled, okay, so it's going to be stable. It's critical to note here, the ones that are going to form positive ions must give away valence electrons, and those would be metals, okay, that would be willing to give away. They will have very few valence electrons themselves. So then saying instead of gaining an extra however many, they can rather just give those away. So which are the ones with the lowest number of valence electrons? B, definitely. D, definitely. Only has got 2. And F, definitely. So we've got 3 options here. B, D, and F. All will give away. For B, it was 1. It would give away that 1 valence electron. For D, it was only had 2, so very willing to give those away. Although, hold on, possibly not, because 2, if I look at it, so D, if I look at it, is actually helium. And I'm going to jump, no, it's not. It would be, jump across. For a second, I thought that was helium. It's not. 1s1, 1s2, 2s1, 2s2. It's beryllium, and it's definitely going to form a positive ion. F, there it was, that's probably boron, and that's going to only have 3 valence electrons, which would give it away. Let's keep going. Comparing elements B and F, which will have the lowest first ionization energy? When I speak about ionization energy, remember we're saying it's the energy needed to remove an electron, to take an electron away, right? So, how would that relate? Well, the focus here is how much energy, how easy or hard is it going to be to take an electron away from an atom? If the atom is small, so let me give myself some space, and I'm going to, at the bottom of the page here, write up lithium, and then directly below it, oh sorry, we don't need a calculator, directly below it I'm going to write sodium. Lithium has its 2 energy levels, sodium has its 1, 2, 3 energy levels. And I'm exaggerating these. That was sodium. Let me redraw the second part because I haven't drawn it particularly well. Let's redraw that quickly. It's going to have its sodium with its 1, 2, 3 energy levels. That's slightly better. To identify here that from the center to the outside and from the center to the outside, it's getting bigger. Why is it getting bigger? Because it's now got an extra energy level. What happens if I'm trying to remove that electron that is sitting there? Which one would be easier to take away? Well, the central nucleus, remember that's the positive, guys. The protons are sitting there. This one's got 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The nucleus is much further away, or that electron is much further away from the nucleus, which is going to mean that it's got a much weaker pull or weaker attraction. So, comparing those two, which one would be the easiest route to taking away an electron? It's going to be for sodium, because the valence electron is much further away from the central nucleus. And that's going to help us answer this question. Comparing B and F, which will have the lowest first ionization energy. The lowest energy, well, we're now looking specifically at B and at F. They've got different numbers of electrons, but think this through. This has is getting to energy level 3, which means the third energy level. In comparison, F is only in the second energy level, which means this electron is going to be further away. So B is my answer. Why? Well, because it has the most energy. Whoopsie. Trying to get fast with my handwriting. It doesn't work. Energy levels. And so your focus here is that the valence electron will be further away from the nucleus, which means that less energy is required to take away that one valence electron. Write down the chemical name for symbol A. So you could do this for all of them, but they're specifically asking for symbol A. I want us to go through this. The quickest way to do it is to jump right to the end and say, okay, where am I looking? I'm looking in group 6, and I'm looking in period 3. So let's have a look at that. I want to look in group 6 or group 16, depending on the periodic table that you're looking at, group 6 or group 16. And I said the third period. So the third row, going back to it, recognize why. We said it's got 6 valence electrons and it's filling the third energy level. So I need to go across here to my periodic table and say, okay, let's find group 16 and let's look for the third energy level. So going 1, 2, 3. It's going to be sulfur. Perfect. We can fill in sulfur, and as the whole name, not just the symbol, which will have the electron configuration simplified to neon 3s1. Well, first I want us to write a neon's electron configuration. There it is. It's got 10 electrons. So I'm jumping across and I'm going to write, well, it's 1s, 2, 2s, 2, 2p, 6. 2 plus 2 is 4, plus 6 is 10. That's neon's electron configuration. What about that extra bit? Well, that extra bit is coming. So that whole thing is standing for neon, Ne, and then it's got the extra bit. So let's have a look at it. It would be, all filling in? No. B, look here, 1s2, 2s2, 2p6. That's exactly what we had for neon, except we have to add the extra bit, 3s1, which is what you've got there. So my final answer here would therefore be B has the same electron configuration there.
I'm sure you've seen the walk together photo on our page. Please post a caption and like the captions that you think are best. The 3 captions with the most likes will each win a pair of tummy tackies. We'll post the winners on Friday, so get to liking and get all your friends to like too. Now it's time to take a break, so don't go away. We'll be right back. Welcome back from the break. I know you can't wait for the term to end and for the holidays to start. This year we bring you revision sessions from term 1 from the 28th of March till the 6th of April. These will be repeats of all the Learn Extra live shows from term 1. These programs will run from 9 a.m. in the morning till 7 p.m. at night. Go to our website learn.mindset.co.za for all the details. But for now, let's get back to the revision.
I've got one here about ammonia. Consider the bonding of ammonia, which is given the formula NH3. Now that's quite an important formula. I would suggest you kind of keep it in the back of your mind because, like your phone number, you're going to use it a lot, so it's a good one to remember. Ammonia will come up quite often, and so it's valuable for you to just pick that formula up and make sure you note it. Identify the type of bonding. So here we're looking, is it going to be covalent, is it going to be ionic, or is it going to be metallic? Well, it's certainly not metallic because metallic bonding would be within a metal, and we definitely don't have metals there. If I have a look at it, let's go and find the different substances. I had nitrogen, which is over here, and hydrogen, which is a non-metal. Watch out for it. It's still a non-metal. I know it's in group 1, but it's a non-metal, and that's why very often they separate hydrogen away from group 1, but it is still a non-metal. So what I want us to pick up here is that we've got a non-metal with another non-metal. So what type of bonding are we going to identify? It must be covalent, because it's going to have to share those valence electrons. And what's going to happen is almost like a little bit of a tug of war. So nitrogen's going to have its electrons, hydrogen will come overlap with it in terms of those outer energy levels. And so they will both have a share of those electrons. How many valence electrons does a nitrogen atom have? So I go across to my periodic table. I've already identified it. There it is, nitrogen 714. It's in group 5. And remember from when we did the periodic table that the group number, group number 15, means it's going to have 5 valence electrons. Why? Because obviously I'm taking away the transition elements. And specifically identifying there that it's going to have its 5 valence electrons, or 5 outermost electrons. So 5 valence electrons. And you could do an energy level diagram if you wanted to work that out, but I can identify immediately just looking at the periodic table which group it's in, and I can tell that its group number will link me to the number of valence electrons. Now state the valency of nitrogen. Well, this is an interesting one because valency is referring to how many bonds it can make, whereas valence electrons is how many electrons this thing has. So I'm going to stop and quickly just draw nitrogen, and let's pick it up from here. Nitrogen, and I'm doing a Lewis diagram, 1, 2, 3, 4, 5 valence electrons. Let's just make those circles a little bit bigger. 5 valence electrons. If it was to bond, we would want to know how many bonds can this thing make? Well, it's going to have to make 3 bonds because notice it's got 3 empty spaces. It's got 3 unpaired electrons. So it must have a valency of 3. It will want to bond there, it will want to bond another one there, another one here. Okay? So it must have a valency of 3. And let's just write out there, valency of 3. Draw a Lewis diagram to illustrate the bonding. Now, I started a Lewis diagram because I know it's coming, but very useful in terms of answering your questions is go and make use of the models that you have. Go and draw an energy level diagram. Go and draw a concentric circle model. Whatever that will help you to identify where the electrons are so that you can very quickly identify the number of valence electrons, the valency, and the type of bonding that's going to be occurring. Okay, so I'm going to start with nitrogen again. Draw a Lewis diagram to illustrate the bonding of ammonia. And ammonia I'm drawing the nitrogen first with its 1, 2, 3, 4, 5. Very useful to work your way around, kind of like the points on a clock or the points on a compass, because it will help you to pick up where the paired electrons are, or the lone pairs are, like the one at the top, and where the unpaired electrons, or if there are unpaired electrons, I should rather say. Because obviously this is just a quick, simple sketch model. It's not the real picture. Remember, the real picture, we're going to have spherical orbitals and dumbbell-shaped orbitals, the sp orbitals. The various different orbitals have various different shapes. And so we're just drawing a simplified diagram, a Lewis diagram, to help us indicate, are there lone pairs, i.e. paired up ones? Are there unpaired electrons? So it's just a quick model. Now I want to draw hydrogen. So hydrogen with its 1 valence electron. And maybe I should draw that as a cross so that you can identify the hydrogen. How will these come together? Well, a hydrogen can share with that one, hydrogen will share with the bottom one, and a hydrogen will share with that one on the side. So, once again, I'm going to draw the nitrogen. 1, 2, 3, 4, 5. And I'm going to just change color and draw in 1 hydrogen there, another hydrogen with its electron there, and a last hydrogen with its one there. So here we have 3 sets of shared electrons, and so if you like, there are 3 covalent bonds, because there is a single covalent bond between hydrogen and nitrogen, another single covalent bond between hydrogen and nitrogen, and another one between the hydrogen and nitrogen. And I think it's important that we add in here, they are all single bonds, but sharing a pair of electrons. Happy with that? I think it's very valuable to start, whenever you draw something like this, to identify at the beginning what the original atoms were. Okay? And then once you've drawn the original atoms, you can then link them up. It's going to help you not make mistakes. And once you've finished, go and compare that to what the formula was. Remember, the formula was NH3. And that would make sense. We've got nitrogen with its 3 hydrogens. So the formula ties up very beautifully there. Excellent. Let's try the next question. Question 2. Consider the compound aluminium oxide. So they've given us the name. They haven't given us the formula. And what do you know? Down the page, they're going to ask us to write a formula. But let's not stress. What we're going to do is go and work it out. So start with identifying the type of bonding that occurs. Aluminium is a metal. Oxide is the ion that forms from oxygen. So that's a metal, and it's joined together with a non-metal. So go across to the periodic table, find them. Aluminium is in group 3, and here on that, if you have a little zigzag line, that's still identified as a metal. And oxygen on this side, a non-metal. So we're identifying we've got a metal joining with a non-metal. The metal is going to be willing to give away its electrons. The non-metal is going to want to take up those electrons. And so this is going to form a positive ion, that's going to form a negative ion, and so we've got definite ionic bonding there. So the type of bonding, it's going to be ionic bonding. Next one. Draw a Lewis diagram indicating the bonding here in aluminium oxide, and then asking us to write the formula. So I'm going to give myself lots of space and start with aluminium. Notice I said to you it's always helpful to start with drawing just where the electrons would be as an atom. Okay? So I'm going to go across to the periodic table, identify it's got 13 protons, and so therefore 13 electrons. I only need to draw the valence electrons. So I'm going to look at the group number, which also happens to be 13, or linking up to group 3. This thing is going to have 3 valence electrons. So let's go across here and draw in its 1, 2, 3 valence electrons. The next one I'm going to draw is oxygen. And oxygen is in group 16, which means it's going to have 6 valence electrons. It's got a total of 8. Check it quickly. A total of 8 protons, so 8 electrons. And so it's going to have oxygen 1, 2, 3, 4, 5, 6 electrons. It's got a valency of 2. It's going to have opportunity to make 2 bonds. But aluminium is going to need to make 3. Well, there's going to be, agreed with me, a transfer of electrons. So I'm going to draw a little arrow along here. 1 is going to fit in there. 1 is going to fit in there. What's the other one going to do? Well, lo and behold, we're going to need to have more aluminiums and more oxygens. So I'm going to start with another aluminium with its 1, 2, 3, and another oxygen with its 1, 2, 3, 4, 5, 6 valence electrons. Now let's go back. That one can fit in there. That one can fit in there. We still have got 2 electrons to give away, so 1 more oxygen is required. Oxygen with its 1, 2, 3, 4, 5, 6. And here we can have the transfer, and there we can have a transfer. And so we're ending up with 2 aluminiums with 2 aluminium ions form with 3 oxide ions. So this formula is coming together, but I haven't quite finished this yet. I want to go across and now write up, okay, well, now I'm ending up with aluminium. Overall, it hasn't got those 3 valence electrons, and so it's lost them and has formed a 3+ ion. But I've got 2 of them, so I'm going to write them both. Aluminium with its 3+ ion. The oxides, well, let's draw them up. Oxygen, 6 of its own plus, and I'm going to write in the little crosses, 1, 2 extra. So overall, it's going to become now a 2- ion. It's got its own 6, and it's taken up an extra 2, so it's performed a 2- ion. I'm just going to repeat that. Oxygen with its 6, and the extra 2, making it a 2- ion overall. And last one here, 1, 2, 3, 4, 5, 6 of its own, plus an extra 1, 2, is forming another 2- ion. This is very, very useful. Notice I've shown the transfer of electrons. I've shown metals giving away electrons to form positive ions, and I'm showing the non-metals taking up those extra electrons, forming negative ions. And remember, positives and negatives are going to have a strong attraction, and so therefore will definitely come together and attract electrostatically. Can we now write the formula? Well, I want us to identify that I had to have 2 of the aluminiums with 3 of the oxygens. So my formula is a ratio aluminium 2, oxygen 3. This is a formula unit because actually this is going to happen on a much bigger scale, and it's not just a molecule. This is going to form a crystal lattice which is going to be a repeating structure. So rather the formula unit would be Al2O3. I'm just going to correct my writing there, aluminium 2, oxygen 3. And you can see why that formula is the way it is. Because we had to have the correct number of electrons being transferred, because the whole point of this is to get filled outer energy levels, right? To make sure we have filled outer energy levels so that these substances become stable.
We've come to the end of our show. Thank you so much, Mindsetters, for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get your notes and to watch the videos from the term. Goodbye.